Okay. Okay, welcome again for this part of the afternoon. I'm very happy to have Tom Lyon here, who actually had a single digit employee number with Sun. So after that, everything went NFS, and now you're going to tell us that it should die. So take it away.
Okay, thank you. Can you hear me okay? Yeah. All right, thanks to the organizers for inviting me, and thanks to Peter Honeyman for twisting my arm to come. I assume everyone knows what NFS is, being a Unix crowd. So this is my short bio. For the purposes of this talk, the interesting bit is that I was at Sun at the beginning. I was one of the NFS architects. I was not one of the NFS implementers. Because my brother Bob was chosen to lead the group, and we were already living together. I figured maybe too much. So I went off and did a bunch of other protocols. Over here we have scribblings of the NFS architecture from the original NFS architecture offsite, which was held at our house. And amazingly, the architecture has not changed. That's mine. The only thing that's changed is this little cloud here has gotten a whole lot bigger. Okay. Oh, I'm told that the NFS Pro side is over here and the NFS Anti side is over here. And I'm sure I'll have enough to piss off both sides. Okay, so the context is it's not all of NFS that I hate. I use it at home. It works great when it's just me and my 5 little devices. But I'm really talking about managing data sets in the cloud. And file systems are great for files, but they don't really give a shit about data sets, collections of files. And there's a lack of capabilities there. So a data set is a big collection of files, and your application cares a lot about the inter-file consistency, but the file system doesn't. In Linux, a mountable hierarchy is a good substitute for a formal data set. Right, so you whip out your USB key, you've got a data set on it, and it gets mounted. And this talk is not just about the NFS, but really about any network file system. I claim network file system is an oxymoron, and we'll get more into that. So I have to mention AI because that's where we are these days. But the example use case is you've got a huge training data set, billions of files, and you've got hundreds of agents frequently updating it and thousands of nodes wanting to consume this data set. How do you keep all this consistent in some interesting way? And if anyone feels like they have that problem, I'm looking for users who have that problem. Okay, so NFS, the good parts. The killer feature is you can rapidly access data sets of arbitrary size. Right? You just mount the data set and pull over what you need. And it's accessible by network oblivious programs. Right? So you don't have to know anything about networking to write a program which may or may not consume network files. That's all great. If you're writing a program that's actually network aware, you should be using network protocols and object storage. It's just where we are these days. NFS is very widely implemented. And there's been a huge amount of engineering put into it. Peter was just telling me how he personally spent $10 million improving things. Other people's money, but it's always other people's money. But the industry has invested hundreds of millions of dollars into making NFS better. But guess what? I think it will never be correct. It will never be fully safe. And this is why we should stop using it. Um, yeah, well, that's the good part. So we're at an existential crisis with network file systems. And the thing is, the greatest learning in parallel and distributed computing over the past 30 years or so has been that shared mutable data is a really bad idea. And we most often hear this in the context of languages, multiprocessing, and threading, shared local memory, where it's like sharing memory is just full of race conditions. You can't even understand the hardware level semantics of shared memory, let alone the software level semantics. Even on an Intel, which has strong memory consistency, you can dredge up cases where it's just completely bizarre behavior. So if you're 100% confident that you know where to put all those atomics and spin locks and all that stuff when you're writing Linux kernel code, then you're in the 0.0001% of the population, right? And you can continue using that kind of stuff. So the shared memory problem is also true when you're sharing blocks, when you're sharing files, even when you're sharing a database. You know, it used to be that people thought, put all your schemas in a central database for your company, that'll solve all your problems. Then, oh, by the way, we really needed to extend the database to have application-aware extensions. And that only went so far. But these days, what happens is you embed the database behind the application. That's the successful model. So there's only one router for the state. So the whole point of a network file system is to provide this hotbed of shared mutable data. And it's just bad things waiting to happen. People are still investing hugely in NFS, right? There's a whole new line of companies like Hammerspace, Weka, Vast Data that all rely on this kind of thing. Amazon has a cloud-managed NFS offering. Anyone using that? No. Yeah, don't do that. So the problem is there is no N in POSIX, right? The POSIX spec was written to also be completely network oblivious. And you know, it assumes consistency. You know, you have this, in those days you had a single threaded kernel that took care of multiple processes contending for a file, right? We can do that. And it assumes availability in that if the kernel crashes, your application also crashes. So they're in the same availability domain. These days, we know about the CAP theorem. In a network, you can't have consistency, availability, and lack of partitioning. You always have partitions because it's a network. So you get to choose between consistency and availability. Sometimes the end user knows what they want, consistency or availability. The software hardly ever knows what it wants because it depends on the end user. In the NFS days, we discovered this the hard way, and we had to do hard mounts to get consistency and soft mounts to get availability. And of course, it depends, you know, are you going to piss off this group or that group? So POSIX is hopeless. It's probably the most frequent criticism of NFS back in the days was it doesn't implement full POSIX. It's like, aside from the fact that it's not possible to implement full POSIX on a network, no one's ever actually read the spec, right? What they're saying is it didn't implement their favorite little feature. So what semantics should these things implement? Should it be the POSIX standard? Should it be a particular protocol semantics, like NFS version 3, 4, 4.2? A particular file system, you know, the dominant ext4. Wouldn't it be great if everything just behaved just like that? Should it implement the full-blown system call interface and nothing else? But every real system chooses a subset of all that and then adds special features. So what it really means is everyone's just doing something different. All these things evolve slowly. And you know, if you're a human, maybe you can figure out when something doesn't work, what the problem is. When you're a program written to depend on 1,000 other layers of programs, which may or may not be doing something with the file system, you can't possibly figure this out. So there's just unsafe things happening all over. So the two hardest problems in computer science, right? Naming, cache invalidation, and off by one errors, right? All these network file systems, they have to do caching, or performance is just terrible. But cache invalidation ends up being both slow and buggy. And over and over and over again, people dredge up bugs in this stuff. And again, even at the hardware level, people are still dredging up memory system bugs, or security holes, and that kind of stuff. So the only way to make caching work is if you never have to invalidate things, which is the right way to go. All right, so this talk is really about what goes on in the cloud. And who is the client in the cloud? We're no longer talking about a person sitting at the keyboard where when the program says IO error and terminates, they can understand, oh, I should plug in the network cable or retry it or try again tomorrow or go home or shoot the developer, I don't know. And people care a lot about file system names, right? That's how you remember where everything is. Programs don't care about names at all. They just want to handle it, do something. People are not restartable, right? If the file system errors out and they lose their full day's work, they're not happy. In the cloud, what you really want is everything to be restartable, right? Serverless functions, containers, whatever. So if something bad happens, you just restart it. And that's the beauty of functional programming, is if you give it the same inputs again, it should produce the same output. If something goes wrong, you just do it again. So this is the way things should be. Developers, of course, are lazy. They want every machine to act like their local machine that they develop on. And so that's the whole success behind Docker and all that kind of stuff. But these days, it really means that what they really care about is everything should be just like my little Linux machine, because that's 99% of the world now. So the way you make cloud scale sharing work is with shared, layered, immutable data. And the success stories are Git, which we all know, Docker files, which we all know. And there's a whole bunch of other more specific things like Delta Lake, Pachyderm, which originally was advertising itself as Git for data. A lot of these things, but almost all of those, or maybe all of those, don't access the data. They require you to copy the data before you do your thing, right? So Git copies everything. Docker copies everything. But the beauty of being immutable is you can cache the hell out of it, you can replicate it. As long as you know what it is, it's never going to change. And you can have as many copies in as many places as you want. And of course, you can't share it until it becomes immutable, right? So git push or git commit or something like that. It's never going to change again. So how would you make a system work that really did all this layering but didn't have to copy stuff? Well, these days, the hot new block level protocol is NVMe over fabrics. And how many people have experienced NVMe over fabrics? Yeah, not very many yet. NVMe is blazing fast storage. They finally figured out they could have lots of parallel queues and lots of deep queues. NVMe over fabrics layers that nicely onto either RDMA or TCP. I hate RDMA, but that's a different story. And it's RDMA is cheap. Yeah, but you get very high performance remote block storage. And in my previous company, we did a fair amount of work with this. It was often a couple of percentage points faster to do the remote access to the same drive because you get a little bit of additional caching and pipelining going. And the beauty of block access is, block semantics are very well defined, right? You can read a block and you can write a block. That's all you really need. If you want to get fancy with flushing and caching and all that, you can do that too. Blocks are aggressively cached, so if you reuse stuff, it's already in your memory. And there's lots of different block storage providers, right? And most notably EBS in the cloud, but even ZFS, you can have iSCSI volumes and stuff like that. So it's everywhere. All the big companies sell it. All the virtual machines are using block device protocols already for this, that, and the other. So block storage is out there, but it's not thought of for use in sharing very much. Now in Linux, there's this device mapper, which is a enormous set of block level utilities in the kernel, including snapshot for copy on write, dynamic extension of block devices so you can have file systems grow forever, multipathing if you want to be able to get better availability out of your connectivity, encryption of different kinds, lots and lots of capabilities. As an aside, over here we have a circle/network disk. How many people use Sun with a network disk protocol? All right. And let's see, you're on the pro NFS side, so that makes sense. So the release before NFS was network disk, and it was this very simple block level protocol. But back in those days, there were no other additional features to manage block storage or block clients or block servers. It was pathetically primitive. So to encourage migration to NFS, a bunch of these buttons were made up. So get the hell off ND. So this is the opposite of my sentiment these days. As an aside, I'm very proud of the trade-offs we made back when we did NFS. But that was 40 fucking years ago, people. Things have changed. So I have calling my proposal BIFs, Beyond File Systems, BYFS. And it's about layered, immutable, block-based file system images, access via network block protocols. You could use iSCSI or NBD if you really want. Copy and write semantics for updating. So when you access your shared space, you get a writable space. It's just that the writes have no meaning until you commit them somewhere. And so you can work all day long as though it's local. It's just when you really want to share it, you have to do something different. No updates until you commit. And then have a naming scheme so that everything can be auto-mounted. So all you have to do is send your buddy in some foreign country /BYFS/UUID at domain, and they can auto-mount that and get the data set, and you're off to the races. But you need a per-domain controller to keep track of where everything is and who's using it, and lots of other features. So one question with copy on write is, do you do it at the block level or do you do it at the file level? And the file level on Linux is this overlay FS, which is a rather indirect descendant of the translucent file system from Sun, of which I am one of the inventors. And it works pretty well, but if you encounter a very large file, like a database or a huge long log file, then you don't really want to copy it up every time you modify it. And so you can do block-based copy on write, and that's available with the device mapper tools. But then you have the question of which of these do you really want to support? And the answer is, I think, is going to be both. So at every layer, provide both a file section and a block section. And a user can put a symlink from the file section to the block section if he has a troublesome kind of file. And so that block section, the database region, I call it, you can also use to address other problems, such as the billion file problem. So when you get to lots and lots and lots of files in a shared file system, one user doing a find can drag you down very bad. Having hundreds of machines all doing the same find because of some script can be really, really bad. So what you really want to do is change find to look in this database so the database can keep track of what's in the rest of the image. And that database gets updated when you do a commit, and so it's incremental updates, and so it's not very painful. And use a real SQL database, and you can have tools that do real SQL queries on the contents of the file system or the data set. And of course, that requires some prescient thinking about what should the schemas be, but that should be manageable. There's the small file problem. You know, every file comes with a bunch of metadata. And if anyone's ever tried to untar a file with a zillion files, you see how slow it is, right? It's doing one file at a time, and each file has to rattle the disk, and the disk gets rattled through the journal, and everything has to be super consistent all the time. And none of that matters if you don't care about the state of the file system until you commit. So in BeyondFS, you know that the files per se never cross the wire, the blocks do. You don't need any of that journaling. Turn off journaling on the file system, and now things can run a heck of a lot faster. And all you have to do is make sure that when you go to commit it, that there's been no I/O errors up to that point. If there have been, then you go back to step one, is restart your function, try again.
Yeah, so how does this commit work? So I understand there are multiple writers.
No, there's,
You copy and write locally, and then
well, you copy, when you access the data set, you're given an additional layer on top of the immutable data set that's yours, your playground, right? So, and that could be local. It looks like it's local, but it's yours to do what you want. And then no one else can see that until you commit, and at that point it's pushed to the domain controller, and other people can see it. And of course there's commit conflicts that are possible.
how do you deal with that?
So anyway, but the point here for small files, this will be faster than what people are used to with local storage, and you get a free transactional file system, right? You do a whole bunch of updates, and the only thing that matters is the commit point. I think I'm getting to that. Anyway, security, Unix user IDs, user-based security, it has no meaning in a network. You know, Linux is finally getting around to fully supporting user ID translation when you do mounts, right? But that's been countless years, and I'm sure people won't be able to get that right. You know, and NFS had the nobody user ID to hack things around. Personally, I run with root, so I can, but it's my fucking machine, right? So in the BeyondFS, everything's done, authentication is done at the dataset level. You do it with SSH keys. So you know what users have access to what. And if they have access to something, they have access to everything in the dataset. Much easier to do security at a higher level. If you care about privacy, which you should, you can have the device mapper crypt layer do encryption for reads and writes. And that's amazingly fast also, with all the built-in encryption these days. And if you really, really care about checksumming, like you're not using ZFS, you can add DM Verity and get cryptographically strong checksumming to make sure that none of the bits have rotten. I talked about naming a little bit, but you know, if you're not a human, the top thing, give me a UUID and a way to get it. And that should work everywhere, including inside containers. And there's ways to do the plumbing, even though normally you can't do any mounts inside a container. If you're a person, then you want some kind of friendly name, and that introduces the whole question of how do you administrate a friendly namespace. And I have no new art for that. It's just a hard problem, and somebody has to do it. Typically, these names will refer to the top of the data set, the latest thing, although each layer will also have UUIDs, so you can go to specific things. And like Git, you should be able to tag things so humans can find them more easily. Put a well-known DNS server in every domain so that people from around the world can find that data set based on its UUID. So to create a data set, you need some special thing to talk to your domain controller. You say, create something of a certain class. The class will determine all kinds of stuff about the policies associated with the data set, what kind of storage backend, other policies, security, authorizations, blah, blah, blah. And again, a lot of work to do here, but basically you're administrating a data set now, not a file. All right, commits and conflicts. So when you do a commit, a conflict is possible. You can do conflict resolution similar to Git, basically. If the files are, if no one's touched the same file, then it's probably not a problem. But this policy, that's a policy which is dependent on the class that you ask for. You could do fancier merges, even for like a parallel HPC file system. You can say, well, if nobody's changed the byte in the file from anything but from a 0 to non-zero, we can still merge things. But if they change from a non-zero to something else, then it's a conflict. So again, this is policy heavy, but no real new magic here. Sort of gloss over the fact that we're still dealing with a network, and networks fail. So block protocols are particularly annoying because they take a long time to report failure when the network fails. I mean, iSCSI was like a minute before it would tell you that the network's gone. I don't know how you improve that, but I think over time it'll get better. But a network timeout will eventually cause an IO error, EIO, right? There's only one program I know of that's ever been written that handles IO errors properly all the time. Can anyone guess what it is? It's very widely used today. It's over 30 years old. No, it's a database, PostgreSQL. They check for IO errors on fsync, right? Which is something no other program has ever done. But anyway, programs are not going to work properly here. Now, when you're a user, when you're the human sitting in front of your terminal and you get some horrible error like that, you have some idea what to do. When you're a program and you get a horrible error, it's like, if you're lucky, you report the error. If not, you just go off into undefined behavior mode, right? I'm proposing a kernel extension, basically a mount flag that says fail hard. If you get an IO error on this mount point, then don't ever return anything except an IO error from that point on. So it sort of force things to fail at that point, because anything past the failure point is undefined. So that would help uncover some of these things. And of course, if BIFS has ever seen an IO error, then it will refuse to commit the data set. Garbage collection is fun. You have all these layers, they're immutable, and at any time you can coalesce a lower layer into an upper layer if you want to do some kind of garbage collection. Or if your list of layers gets to be way too deep, you can just coalesce as much stuff as you want, and it doesn't change the contents or the meaning or the semantics. You do have to be careful about who is currently caching that layer of stuff, because you're creating a different layer with the same contents. So you have to keep track of all the upper layers and how many users and whether or not things are tagged. And this is really fun. You can do lazy unmounts. So if you're repeatedly doing stuff that needs a lot of these data sets with an arbitrary number of layers, you're only ever changing the top layer. And you can mount it, change it, commit it, go back to the beginning and do something else. And all those lower layers are still mounted and cached and available in your memory. So things go really fast. You just do lazy unmounts every 10 minutes to see if you can get rid of something. So I'd say summary, network file systems are inherently unsafe. The CAP theorem will bite you, and there's no escaping it, because you never know what the user really wants, availability or consistency. No one knows what semantics the file system really offers, and there's no tools to check to see whether your library is doing something weird with the file system. I got burned with the build root system doing some embedded Linux thing. It didn't work when it was on NFS. I have no idea why. It's buried deep in there somewhere. Block storage is cool, and it's very well defined semantically, very broadly implemented. It's very fast, and it lets you to do all kinds of groovy stuff, both locally and on the server side. So let's get beyond file sharing. So, status. This is a call for collaborators. I need lots of help because I don't program anymore. This is a problem. I think I was the number 3 person to be named a distinguished engineer at Sun. That was like 35 years ago. And that was the end of my engineering career. I was just extinguished engineer. So I'm really looking for people who might appreciate this as a solution to their problem, and for people who might get excited working on such a thing, because I have all the answers in my head, all the answers. That's it. Questions?
Okay, thank you. I really can understand that there's questions. Yeah. Oh.
Don't the Oxide people maybe have some use for this? So they could chime in, so to say?
Yeah. I was trying to get Brian to listen to an early dry run of this, but he's been too busy. So. But if you have an in there.
You were called a distinguished guest, friend of the show on one of the podcasts, so I thought you had the way in.
Or maybe this conflicts with what they're doing. I don't know.
Yeah. I knew that.
I have more of a comment than a question.
A cormorant.
It's a famous way to, yeah. So, Tom rants about NFS on Mastodon and other things. And last year, he was doing so, and Kuhn here challenged him to write up his thoughts and bring them to NLUUG, which he refused to do because the fall conference was, right around the corner, and it was closed anyway. But he suggested that, maybe I could do that for the spring conference. And I saw that, and I said, well, I would attend that talk for sure. And then it looked like Tom was actually going to come through and do it, and I felt like, this is actually why I wrote my talk. So I may have goaded you into coming to NLUUG, but you also prompted me to come back. So I brought you a gift.
Well, that's the beauty of collaboration, as you get more stuff going on.
If I can get it out of my...
Uh-oh. Oh, sweet. This is like the Bell Labs reprint of
It's
the John Lyons
It's
book.
the original.
Common- Two of them? Two of them?
Well, there's the commentary, the source
Oh,
code
of
and
course,
the
of
commentary.
course.
Yeah.
Wow, thank you. Of course, it's not the original Australian one. Right?
No. This is the
But-
original. The,
Well, it's
later-
got Bell Labs cover on it, though.
The later book was the reprint after.
No, I know,
Lyons.
but it's
So you can see here that
the content is original, but the original.
I had to sign this out of the Bell Labs library and promise to return it.
Yeah. Sweet. Whatever. Thank you very much. For those of you who don't follow me on Mastodon, I do a lot of computer history stuff, and I have a lot of cool artifacts. So these more cool artifacts.
Okay. Question. How long are you already advocating for this new setup, and how many collaborators did you already found?
Are you volunteering?
Maybe after this answer.
This is my first public appearance, right? So it's just me right now.
You should do it more often.
I should, but that's the problem being, well, pretty much entirely retired and enjoying life instead of doing engineering, which I vaguely remember.
Yeah, I was going to ask whether there was already code, so not yet.
Back in the day, and I don't have a lot of experience with it, but I can vaguely remember there was something like a shared file system clustering with VMS, HP VMS, that you could have a drive with a file system shared by two servers that seemed to work. And then
Right.
there's also the Apollo workstation that had sort of a transparent network file system, which to me is still the golden view of what NFS should be like.
Right.
But maybe they had problems that I don't know about. So
Well, the VAX cluster ran on a special interconnect, which you kind of assumed would never fail. If it did, bad things happened. And similarly, Apollo, I don't know what their access semantics were because it wasn't Unix.
// was the root of the network.
Right. But probably they also had this partitioning problem, especially because back in the day, hardware hardly ever worked for very long. All right. But there's lots of other examples. Like even today, Linux supports cluster file systems, GFS and OCFS2, that share directly a disk, kind of like the VAX did. But the amount of metadata that has to happen between the nodes to make anything work is just frightening. So enormous amounts of code which cannot be proven correct.
Any other questions? Well, let's thank the speaker again.
Okay.